Dear students, in last class we discussed about the time setting and plug setting of overcurrent relay. In today's class, we shall have a discussion on directional overcurrent relay. Definition: unlike overcurrent relay or non-directional overcurrent relay, the directional overcurrent relay operates for a particular direction of overcurrent flowing through it, and it restrains from operation for the other direction of overcurrent flowing through it. Directional overcurrent relay is a type of overcurrent relay that operates for particular direction of overcurrent flowing through it. Directional overcurrent relay does not operate for the opposite direction of overcurrent flowing through it. To understand forward and reverse faults, let us consider a transmission line fed from both the ends. Now this transmission line here is having a circuit breaker at the left bus, and that circuit breaker is associated with relay R, which is fed by a CT and PT. The voltage fed to the relay is VPC and current fed to the relay is IPC. Here I have marked forward fault and reverse fault. We can interchange these forward fault and reverse fault also. Let us say a fault occurs to the right of circuit breaker. In that case, through the CT, current will be flowing towards the fault. That is from source 1. And the source 2 will also feed the fault. Instead of a fault occurring here, the fault may occur before this circuit breaker. The fault may occur before circuit breaker. In this case, what happens is source 1 will supply part of the fault current and source 2 will also supply part of the fault current. You can observe that the part of fault current fed by source 1 is now not going to flow through the CT, but the part of the fault current fed by source 2 is only going to flow through CT. So the direction of current through the CT is now going to get reversed. But the voltage measured by the PT will not change its polarity. Its polarity remains the same. What is happening is only the direction of current through the CT is changing. For fault after the CT, current is towards right. For the fault before CT, the fault current is towards left. Now, the fault that is after the CT or circuit breaker is called as forward fault, and the fault that is before CT or circuit breaker is called as reverse fault. Even if I exchange the positions of forward fault and reverse fault, then also when the fault moves from front of the relay to the back of the relay or back of the relay to the front of the relay, there will be change in the direction of current flowing through the CT. Hence, we can say that there is change in the direction of power flow, and that power flow is nothing but fault power flow. If we make use of non-directional relay, then it will be not possible for it to detect the change in the direction of fault current, because we know that driving torque developed by overcurrent relay is proportional to product of the two fluxes produced by two coils multiplied by sine of angle between two fluxes. Since the two fluxes are directly proportional to the same current in overcurrent relay, the torque becomes directly proportional to I square. For positive direction or negative direction of the current, the torque remains always positive. That means the overcurrent relay, which is fed with only the current, cannot have directional feature. So in order to have directional feature along with overcurrent feature, we must have two coils in the relay, and one coil of the relay should be fed with current and the other coil of the relay should be fed with voltage. Now let us study the theory of such relays. Theory of directional overcurrent relay. A directional relay or a directional overcurrent relay can be compared to a contact making wattmeter. You all have studied wattmeter construction. Wattmeters are used for measurement of power in electric circuits, and the deflection made by the moving system is proportional to the power flowing through it. A wattmeter develops maximum positive torque when the current and voltage supplied to current and pressure coil are in phase. If we define the maximum torque angle MTA as the angle between voltage and current at which the relay develops maximum torque. Then a wattmeter can be called a directional overcurrent relay. With MTA of 0 degree. The figure below shows the block diagram of directional overcurrent relay. It is current coil, it is pressure coil, variable resistor and capacitor. Voltage from potential transformer, and here it is current from CT, call it as ICC. Strip output, is called as induction cup. Current through pressure coil is called IPC. Now here is the phasor diagram of directional overcurrent relay based on induction principle. Voltage applied to the pressure coil of relay is taken as a reference, that is VPC is reference. Current through the pressure coil is IPC. It lags the pressure coil voltage by an angle of theta PC. Flux produced by the pressure coil is proportional to and in phase with pressure coil current IPC. So we have shown 5 PC in phase with IPC. Let us say current through the current coil of the relay ICC is leading the voltage VPC by an angle of theta. The flux produced by current coil is proportional to ICC and is in phase with ICC. So phi cc is shown in phase with ICC. And now here a maximum torque line is shown, and the maximum torque line is at an angle of tau from reference, that is from VPC. The operating torque of the directional relay can be expressed as operating torque T operating proportional to phi PC into phi CC into sine of angle between the two fluxes phi PC and phi CC is theta PC plus theta. So sine of theta plus theta PC. From phasor diagram, theta PC plus tau is 90 degree. Therefore, theta PC is equal to 90 degree minus tau. Therefore, T operating becomes phi PC into phi CC into sine of, in place of theta PC we will substitute 90 minus tau. So theta plus 90 minus tau. That is phi PC into phi CC into sine of, grouping theta and tau as theta minus tau and writing 90 degrees separately, we get 5 pc into 5 cc into sine of theta minus tau plus 90 degree. Sine of theta minus tau plus 90 degree is cos of theta minus tau. So you can write 5 pc into 5 cc into cos of theta minus tau. Bringing proportionality constant k1 here, we can write operating torque as 5 pc into 5 cc into cos of theta minus tau. But 5 pc is proportional to vpc and 5 cc is proportional to icc. Therefore T operating will be equal to K2 into VPC into ICC into cos of theta minus tau, where K1 and K2 are constants of proportionality. From expression for torque, when theta becomes equal to tau, cos of theta minus tau becomes equal to unity, or torque becomes maximum. Also, when ICC is shifted by plus or minus 90 degree from maximum torque angle position, the torque becomes zero. Therefore, plus or minus 90 degree line from MTA gives us a boundary line. That is, the straight line shown here at 90 degree to this MTA position has to its right the trip region and to its left restrain region, because along this line the torque is equal to 0 Above this line or to the right of the line, torque is positive, and to the left of this line, the torque is negative. That is why it is called as restraining region. Therefore, a line drawn at plus or minus 90 degree to MTA position has trip region to its right and restrain region to its left. So when fault moves from front of the relay to the back of the relay, the direction of current gets reversed in this way. And for the current phasor in the restrain region, the torque developed by the relay is negative, and hence the relay restrains from its operation. When fault moves from front of the relay to back of the relay, the current ICC falls in restrain region. Hence, relay does not operate. As it develops, negative torque. Dear students, I will stop the class here and continue in next class. Thank you.